Good morning, guys. Jeremiah here again. One of the last videos I published and put out there recently was called The Power of a Diagnostic. And basically I went ahead and I listed a bunch of pros and some of the cons behind why we would or would not want to do one of these full diagnostics each and every time we're out servicing our customers' HVAC equipment. Today I want to go just a step further and actually show you a real diagnostic from an equipment, from some equipment we installed about a year ago or so. This was the day of the install. Our installation team goes ahead and does a full startup on the equipment and make sure we get all the numbers so we know that the system's operating perfectly on the day of the install. Behind me you'll see, again, I took out the customer's last name and address. However, it is a real installation. It was done last year, approximately this time, about a year ago or so. Long story short is we went ahead and, just like I discussed before, we had pretty much filled out every single one of these. There's a few that aren't filled out. We're going to go ahead and fill most of those in now because in the field the guys sometimes don't actually take the numbers and work them into the equation to actually get a final outcome. However, it's pretty simple. We're going to talk about that today, as well as go through each one of those formulas today. First thing I'm going to do is I'm just going to go through, I'm going to call out each and every parameter that we actually check while we're out there, and I'm going to give you the numbers, and then I'm going to talk about 2 or 3 different equations we use on a day-to-day basis, or we can use on a day-to-day basis, to actually give us an idea of how the equipment is actually working and is it doing what it was designed to do. So we're going to go ahead and start out with the type of equipment. So we're in South Florida, so this was an air handler. There was no heat outside of electric heat installed into this unit, but we did go ahead and put a heater into the unit, and these are the numbers for that. So this is a 24 ACB 748. For those of you that aren't familiar with carrier nomenclature, that is actually a 4-ton, 2-stage condenser attached to a true variable speed air handler. And one of the first things our guys do when they're out starting a unit up is we actually check the heat, 1, to make sure it's wired properly and working well, and 2, because it's an easy way to determine CFM. All right, so the first equation that we're going to get to then is actually called the heat rise method for calculating CFM. Pretty simple equation. And basically what we got to do is we take our total BTUs in heating, and we're going to actually take that and we divide it by 1.08, which happens to be the sensible heating constant. Anytime you want to find out what sensible heat, you're trying to figure out what sensible heat is actually costing you, it's 1.08 is your constant. And then we go ahead and divide that again by the actual temperature difference, so we can see how much heat is gained, or actually heat in that case, because it's called the heat rise method, how much heat is actually gained by the air as it passes through. That will give us an idea of how many CFM we got. So in this case here we have, again, we're going to take a voltage, because the first thing we need to do is find out how many watts we're actually using in the heating mode. So we take voltage at the air handler, which you can see here. If you can see it, it's kind of small probably on the camera, but it's 247 volts. That's a little high for residential, but we do see that number quite often, especially as we get further out west here in South Florida. So 247 was the voltage recorded at the air handler, and the amperage, that's the amount of heat actually being, that's the amount of electricity actually being used by the heater during operation, was 39 amps. So a real simple equation, amps times volts equals watts. So we try to figure out what the watts are. So we're going to take 247, we're going to times 247 by 39, and we're going to come up with the watts. I'm going to pause to do the calculation. I'll be right back. All right, gentlemen, I'm back. I've done the equation. 247 times 39 gives us 9633. That's rounded, but that's 9,633 watts. We're going to go ahead and take that and actually convert that to BTUs heating. And once again, I'm going to give you another constant. So anytime you want to come out with BTUs in heating, you're going to use 3.4 as your constant. And you're going to take your watts times 3.4, and that's going to give you your BTU in heating. Watts, 96 9633 in this case, times 3.4 comes out to be 32,752. I'm going to get those numbers here written down. So again, 247 times 39 gives us roughly 9,633. 9,633 times the 3.4 to give me my total BTUs in heating is 32,752.2 was the number that I got. And once again, we're going to take that and we're now do our heat rise method, and now we're actually going to take our 32,752.2. We're going to divide that by 1.08, and then because 1.08 is my constant sensible heat factor, and then we're going to once we've done that, we're going to divide that by my temperature difference, which in this case is 22 degrees, 76 going in, 98 coming out. That leaves me a 22 degree temperature difference. And when we do that, we're actually going to come out to 1,378. That's CFM. That's how much airflow this is actually moving. I went one step further and took 1378, divided it by 4 to come up with 345 per ton. This system is more than likely set to nominal airflow, which is approximately 350 CFM per ton. And you can see we're getting 345, which is pretty darn close to where we're supposed to be. Tells me my AC is at least moving the airflow that I am required. This number, we then go ahead and just take this number, 1378, because we're going to use our next equation. And we're going to move this number down here into total CFM. Again, that's just the number. We're just moving it down. 1378. The next thing we're going to do with this diagnostic is actually find out, is this removing the right amount of BTUs in the cooling mode. Now, for those of you that aren't super familiar with air conditioning, there's two types of heat removed during the air conditioning process. Sensible heat, which is the number that we actually can see and or sense, the number that we see on our thermostat. That's considered sensible heat. And then there's latent heat. And believe it or not, I get guys kind of chuckle when I say this, but latent heat is the amount of water that's actually being removed from the air. So literally, the water from your drain line is heat being removed from your air in the form of moisture. So as we send warm, moist air across an evaporator coil, a nice cold evaporator coil, what happens is it lowers the temperature of the air. Lowering the temperature of the air forces the air to get rid of some of its moisture. That moisture is then collected onto the coil, goes into the drain pan, and drips out of your condensate drain line outside. That number of latent heat or hidden heat and the number of sensible heat combined is total heat or enthalpy. That's the total amount of heat removed in the air conditioning process. To go ahead and take this to the next level once again, we're going to take our total CFM, which we just moved down right here, total CFM. All right, and there's another equation we're going to do. In a second, I'll write all these equations on the whiteboard and I'll let you see them. As a matter of fact, I'm going to do that now, so I'm going to pause the video. All right, hopefully this shows up nice and clear. Went ahead and just wrote the few equations that we just were discussing and talking about. The first one here is actually how to determine watts from our amperage and our voltage. The reason we choose these numbers, guys, amperage is typically very, very easy to get in the field. It's as simple as taking your meter, the ammeter that you have, clamping it around your common wire. It's going to give you amperage for that particular component that you're doing. If you want to do the entire air conditioning system, you just go to the power wire coming into the unit itself, into one of the two wires, clamp around that wire. It's going to give you total amperage. Amperage is then, again, very easily compared to voltage. Again, easily found with a voltmeter. Simply take your voltmeter, go from line 1 to line 2 for air conditioning. It's going to give you your voltage. Your voltage times your amperage is going to equal watts. That's what we were discussing over there, which is why we can turn on the electric heater, get a wattage of the heater while it's running, get a voltage of the air handler, and then just times those together. It's going to give you watts. Watts times 3.4. You can see, guys, I squared around the 3.4. That's because that's one of our constants. watts times 3.4 gives me BTU heating, and then BTU heating divided by 1.08 divided again by the temperature difference during that heating process equals CFM for that equipment. So that is a good way to determine CFM in air conditioning. All right, went ahead and drew a few more formulas here on the board, as well as created a small key so we can kind of keep our constants in order. 3.4 is my watt to BTU constant. Again, watts times 3.4 equals BTUs. 1.08 is my sensible heat constant. BTU H, which is figured out once we know watts, times 1.08, which is my sensible heat constant, times my temperature difference is going to equal my total CFM. This, again, right here is your heat rise method for solving for CFM. Once we have CFM, we can actually take that, times it by our next constant, which is our total heat constant. So that's total heat removed constant, times our change. This is delta H, or a change in enthalpy. And we figure that out by getting both a dry bulb and a wet bulb, which I'll show you on our diagnostic here in a minute. We take both of those, plot them either on a psychometric chart, or you can use a psychometric app. Plot them into the psychometric app. You'll get it both. You'll be able to easily determine total heat in the return air, total heat in the supply air. Compare those two numbers. It's going to give you a change in delta H, or a change in enthalpy. And when you plug in the rest of these numbers, your CFM that you solve for, your change in enthalpy that you solve for, you'll be able to solve for BTUs in cooling. We're going to go back over to diagnostic and do that. All right, back again, guys. Not sure if you can see these numbers down here. However, what we're looking for is return air or entering air dry bulb, return air or entering air wet bulb, supply air or leaving air dry bulb, supply air or leaving air wet bulb. Those numbers are 76, 62, 50.6, and 50.3. I went ahead and took those numbers and actually plotted them here on our psychometric chart. So we start with the return air, 76 dry bulb, 62 wet bulb. If you haven't used one of these before, dry bulb is right here on this line down here at the bottom, and your wet bulb is actually along this curve on the top. So what we do is we take 76, we'll follow this over to 75, 76, we're going to follow this line here, and our 62 wet bulb, we follow up on this curved line here, 60, 61, 62. We're going to go where those two lines intersect, right there. That right there is going to give us our plotted point for our return air. We can then take that and follow it back past the wet bulb and into the enthalpy section, and we come up with a 27.7 enthalpy. That's total heat in your return air. We do the exact same process for the supply air, which happens to be 50.6 and 50.3. This is supply air or leaving air dry bulb, supply air or leaving air wet bulb. We take and we plot those two numbers. We're going to come over here to 50, and it's 50.6, so we're going to kind of go right in between here. And same deal here, we're going to go 50, and it says 50.3, so it's not quite in between, but a little before the halfway mark. And when we come up to those two numbers, you end up right around here. And once again, you follow that out, 20 to 21, so we're at just below that 20 and a half, so 20.4. So 20.4 is the total enthalpy of my supply air. 27.7 is the total enthalpy of my return air. Just to put that into perspective, guys, we're taking temperatures at the return air, so just at the bottom of the air conditioner if we're talking about a vertical air conditioner, and then just at the top. So your air handler might be 60 inches high. So from this point to this point, that is the amount of heat that we have actually removed out of that air in just that small time frame. Again, all we're doing is bringing air across a cold coil, and that's forcing both sensible and latent heat to be removed from the air, which we are dumping back into the space. That process happens over and over as we exchange all the air in the home over and over. When we come up with these two numbers, that's going to give us our delta H. All we're doing to get that is, again, we're just subtracting our return air enthalpy from our supply air enthalpy. So 27.7 minus 20.4 gives me 7.3. Then we're going to go ahead and take that and plug that back into our formula that we just showed you on the other board. So that formula was CFM times 4.5 times change in H, or change in enthalpy, equals BTU cooling. And again, remember, we got that CFM earlier of 1,378, which we brought down here. So you take 1,378, you times that by 4.5, which is our constant, and you times that again by the change in enthalpy, which we just found, 7.3. And just so you guys know as well, not everyone has these out in the field, and it can be a little cumbersome. Plus, when these are smaller, they're even more difficult to follow with your eyes. There's plenty of psychometric calculators out there in app form. I think the one I'm using is called Psychometric Light or Air Light Psychometric Calculator. Basically, you plug in your altitude wherever you happen to be. We're in Boca Raton. We're basically sea level. I think our official altitude is 13 feet. So when I did these calculations, I used my psychometric calculator. I put 13 feet into my altitude, and then I just plugged in my dry bulb, wet bulb, and then again my dry bulb, wet bulb for the supply, same as the return, and just compared those two numbers. When you actually do the math for this, you go ahead and take that CFM of 1,378, times it by 4.5, times again by the 7.3 that we discussed. We actually come up with a number for BTUs, which I'm going to go ahead and place right down here. My total BTUs removed are 45,267.3. At the very beginning of this presentation, I told you this was a 4-ton unit. 4 ton is 48, actually represents 48,000 BTUs. Considering we're doing 45 here, I would say we're pretty close for a 4-ton. I would call this unit good. There's also, you also have to take into consideration, guys, that, you know, if you didn't wait quite long enough for your temperature probe to get down, not to mention that it's constantly changing. So as we're removing heat, the amount of heat coming in changes. So all those variables leave you a little bit of wiggle room, guys. But if you're within a couple of thousand BTUs of what you're rated for, you would probably call that good. So I wanted to go ahead and talk about one last one. So often we hear, especially as we're putting the newer, more efficient equipment, which is actually designed to run longer, to provide additional dehumidification for the customer at a lower amount of electricity output. I also oftentimes get customers telling me, I feel like the new air conditioner is running longer than the old air conditioner, and therefore in the customer's minds they equate that to costing them more in electricity. However, if we've cut the amount of electricity used in half and increased the amount of time by 25%, there's still cost savings in electricity. So I wanted to show you a real easy way to figure out what it's actually costing a customer to run their air conditioner, so you can put a perspective to them what it actually is costing. Thanks. Okay, sorry about that. I wasn't sure if the camera had actually turned on. The last formula we're going to talk about is a way to figure out how much electricity you're actually using per day, per month, per hour, etc. So basically we're going to go back to our amps times volts equals watts. Amps times volts equals watts. Watts is going to translate to every 1,000 watts is going to be a kilowatt hour. So wattage, so to convert watts to kilowatts, you're basically going to just divide by 1,000. So your amperage times your voltage will equal your total watts. Watts divided by 1,000 gives you kilowatts, or kilowatt per hour. Once you've got the kilowatt per hour times the amount of hours you're actually running the air conditioner, which oftentimes we have to guess that, or you can put a data logger in and actually track the amount of time and get an average. But you take your kilowatts times your hours divided by 1,000, it's going to give you kilowatt per day. Your kilowatt per day times 30 days is going to give you kilowatt per month. Your kilowatt per month divided by the cost of a kilowatt hour is going to give you your energy cost per appliance. We're going to take that and we're going to apply it to the system we just discussed. All right, using the numbers from the equipment that we just installed, we've been using for our example this entire time. I've got 13.8 total amperage outside, that's at the condensing unit, and I've got 0.45 inside on my fan motor. That's going to give me a total of 14.25 amps while running. We take that number, 14.25, and we're going to times that by our voltage. Amps times volts is going to equal our watts. We're going to get 3,056, etc., which actually is going to come out to, after we divide it, we're going to then take this number and divide this number by 1,000. So you're going to get 3.56 kilowatt hours. I then went ahead and just got a random number. I said, let's imagine we're running this air conditioner for 10 hours a day. We are here in South Florida. You times that by 10, you're going to get 3,056. You're going to go ahead and then take that, and you're going to take that and you're going to times it by 30. 3,560 times 30 days in a month. It's going to give us, so we end up with 35.6 per day. We end up with 3,600 per month. If we take that and we times it by the average electricity bill, which is about 14 cents, we're going to come out with $149 for the month. This air conditioning system, this 4-ton air conditioning system, running 10 hours a day for 30 days in a row, is going to cost them about $150 a month. Again, guys, a real easy way to show a customer what it's actually costing them per month. I hope this video was helpful. Any questions, please comment them down below, and I'll address them later. Otherwise, have a great day. Thanks. Bye-bye.